I'm Doug Clinton, co founder and partner at Deepwater Asset Management. And this is the Deload Podcast, where I interview founders, builders, and CEOs of frontier technology companies transforming how we live. My mission is to educate you as I educate myself about where the world is going. Today, I'm joined by Gordon Wilson, the CEO and co founder of Rain AI. Rain AI is making artificial brains via advanced computer chips. Rain is also a holding in the Deepwater venture portfolio. Gordon and I talk about what it takes to build an artificial brain, including the idea of radical co-design between AI algorithms and hardware, and also why our current computing paradigm isn't enough to take us to the AI future that we all imagine. Now, here we go with Gordon. All right, Gordon, thank you for talking with me today. I'm excited to educate everybody about what is happening in AI, really on the edge of AI compute. So let's start at the very beginning, which is, Rain has this incredible mission to build, an artificial brain, basically. And the mission is to solve a specific problem with that brain, which is the cost of AI. So talk a little bit about, that mission up front. Why do you think AI is so expensive right now? And then we can get into how you're trying to solve that problem.
Yeah, no, it's a great place to start. So, as you said, our mission is to build an artificial brain. All products in our roadmap are what we consider artificial brains, so efficient learning machines. And the brain is our inspiration because the brain is about 1,000,000 times cheaper, more efficient than today's best infrastructure for artificial intelligence. It is so much cheaper from every dimension, from power, from size, from data efficiency. Our brains learn with so few examples. Contrast this to, the neural networks that support things like ChatGPT or AlphaFold or the computer vision models that run on autonomous vehicles. It's vastly more expensive. And it's fundamentally because of the infrastructure, because of the hardware that this is run on. And that hardware today is NVIDIA GPUs. GPUs are great, given what they are. They are digital computers. They're von Neumann machines. They separate memory and processing. But as a result of that, they're not like the brain in the way they process information. GPUs are the best available today, and there was a very lucky moment in history about 11 years ago when NVIDIA could capitalize on to now become this trillion-dollar company. But the NVIDIA roadmap and the GPU roadmap will not take us to truly autonomous machines. We need hardware and we need systems that look much more brain-like and process information in a way that is far more natural and native to a neural network.
Can you talk a little bit about the costs maybe that you're seeing today with some of your customers that you're speaking to? What are they thinking about in terms of how much it's costing for them to train models today and run inference? And where do you think that ultimately can go if we solve this von Neumann bottleneck problem?
Yeah, so cost is a bottleneck at every form factor of artificial intelligence, from the far edge to the hyperscale data center. To train ChatGPT and to deploy ChatGPT is tens of millions, if not hundreds of millions of dollars, taking into account the full continuous inference costs. The cost of training for those large language models is the reason why all of these, LLM Gen AI companies are raising multi-$100 million rounds. It's to ultimately funnel money back into NVIDIA's pockets to support that infrastructure. But it's not just at the data center, and it's not just, limiting there. Like, there's huge environmental consequences that we need to consider at the data center. But when you go to the edge and when you start to think about low power devices, untethered devices, this is a fundamental bottleneck to advancement on the edge. We have what one could consider level 5 autonomy, cars driving around San Francisco, but they have a mini data center on top of every car. And they can drive because they've mapped every single corner of the city precisely, but it is orders of magnitude away from being economically viable as an actual taxi service. that is the cost of compute that is limiting that. Another limiting factor, training. So the training costs are very high. Inference costs are also high, but training is especially high. And as a result of that, today people consider training and inference to be these really separate problems that require separate infrastructure. Any models that you really run at the edge are inference only. They're not learning on the fly. So if we want to make, and we do want to make machines capable of learning on their own, so they can adapt to changing environments, so they can become personalized to their users, so that personalization can be private and secure. Machines, just like humans, will need to be able to learn from their experiences continuously to be truly intelligent. And that means we need to make training cheap enough that it can go into low power footprints. And that is one of the core problems that we're solving here at Rain.
One of the things I always say when I talk to other people about, what Rain is doing and even just broader visions on AI is that unless we figure out a solution to the problem that you're describing, which is the cost to do training, you can't really reach AGI, right? There is a cost bottleneck, to your point earlier about getting to that level of intelligence. I mean, is that the right way to frame it? Is, look, unless we solve that, and there are other problems related to getting to AGI, of course, but unless we solve that cost problem, we can't get there, even if we somehow solve all the technical problems too.
I think that there is a non-zero possibility we could build an AGI with von Neumann computers, but I think it could consume more energy than we have available today. So we would either need some radical rethinking of energy, or, more importantly, we need to make the cost of compute itself radically cheaper. But when I think of AGI, like true AGI is not just something that's locked into a data center. It's something that is an agent in the world that has autonomy to make its own decisions and to explore. And from that definition, certainly not. There is no way to build an AGI. There's no way to build C3PO with GPU infrastructure. We need something that is an artificial brain to actually get there, for autonomous general intelligence to have really capable independent machines.
Yeah, it has to be able to learn and act just like
Yes.
a human brain. And so maybe let's go down that thread a little bit more. I mean, we were talking some about training and inference. Your approach is unique in that you're trying to do both on one chip. And as you kind of alluded to, a lot of other maybe approaches in the space are looking at it as a separate problem. There's obviously a lot of companies, I think, that are focused on perhaps just inference first, because it seems, whether it's true or not, it seems like it may be a slightly easier problem to solve. But why do you think it's so important to be able to do both things on a single chip?
Well, there are a lot of reasons why, and I'd say there was a great quote from Mark Andreessen recently where he said, "Whoever can solve and integrate training inference into one platform has solved $1 trillion problem, or will become $1 trillion company." And to have trained inference in the same platform is necessary, because they really aren't, like, we've only artificially essentially separated these into problems because of the cost requirements. If you want just good inference, you actually have to have some ability for training, because you want model fine-tuning and kind of maintenance of the model so it can keep high accuracy. So they really aren't these separate problems. They're so fundamentally intertwined that, one problem that people face when they separate it and you have two different pieces of infrastructure for your training and inference is that there's mismatch, and that inference model will degrade and be subpar because of just that space between where you are training that model and where you are deploying it. A lot of different companies that have tried to develop new inference hardware have faced this challenge where there's this mismatch. But so there's this challenge from, like, a how do you build it perspective, and really excited to dive into talking about how we think about algorithm hardware co-design and algorithm hardware integration. But again, it's the consequence of integrating training and inference means that I think that that's just what true intelligence looks like. It's adaptation, it's personalization, it's continuous learning from the sparse signals in the real world. That is what's going to be necessary for us to build fleets of robots that build all of our buildings and perform all of our or become all of our electricians and our plumbers and our drivers. This is critical to realize full autonomy, because the real world is dynamic. The real world changes, and these machines need to be able to learn in order to respond to them.
That's right. And I think if you keep the human brain as sort of the inspiration for where we need to go, to your point, it makes total logical sense. You wouldn't want to separate a person's ability to learn and then act. That doesn't make a lot of sense. So talk about, you referenced it just a minute ago, this idea of sort of radical co-design, because I know that's your approach to it. What does radical co-design mean?
Yeah, so radical co-design means looking at the hardware, the algorithms, and the software, not as separate problems, but as one integrated problem. And that's because it is really one integrated problem. Jeff Hinton talked about he called it mortal computation, what we want to ultimately get to, when he at his NeurIPS talk last November, I should say. And in that announcement, he had one reference to hardware, which was our work at Rain. And he talked about mortal computation because when he thinks of the brain, when one looks at the brain, there isn't a separation between the hardware and algorithm, the hardware and the software. They are so intimately integrated together that they're fundamentally inseparable in the brain. And contrast that to the way we build AI today. People build a GPU, NVIDIA builds a GPU. It's supporting more compute, it's at the smaller geometry, it can do more. But then someone else at a layer way above that is building a neural network and training a neural network and thinking about that algorithm of how you train it. The separation between the algorithm, which exists today in a pure software abstraction, and the hardware that's actually running, the electrons that are doing this computation, is so large. And that creates that's one of the reasons why this is so expensive. So we want to close that gap between the algorithm and the hardware, integrate them together, so you can actually have much, much, much cheaper artificial intelligence. So what does this end up looking like in practice? And I think it's actually worthwhile to talk about algorithm hardware compatibility in the context of NVIDIA, and then again also contrast it with how we're doing it. So obviously, NVIDIA is the world's first trillion-dollar semiconductor company. They became that, not surprisingly, the first quarter that their data center revenue exceeded their gaming revenue, driven by artificial intelligence. But when did AI actually become the thing at NVIDIA, and how did that happen? So we got to go back to 2012. 2012, there was this thing called AlexNet, and it was this marriage of two technologies that had existed for some time before that became the seminal moment of the era of deep learning. Now, those two technologies were a training algorithm called backpropagation, which was conceived in the mid-1980s and popularized by Jeff Hinton, and the hardware, the GPU. And what made AlexNet special, because it was the best computer vision model that had ever been developed at that time by a long margin, was that they used multiple GPUs basically to scale out and build a bigger neural network that was a smarter neural network. It was this algorithm hardware compatibility between backprop and GPUs. And since 2012, every major breakthrough, whether it's AlphaFold for protein folding, or CNNs, or recommendation engines that drive revenue at Meta, or now ChatGPT and all the LLMs and generative AI, they've all been built with this combination of technologies: backpropagation as a training algorithm and GPUs as the hardware. Now, the thing is, this is suitable as long as we can keep scaling on Moore's law, but, well, even so, not really, because it's so damn expensive. So we need to find new algorithms and new hardware and find ways that they can be intertwined together and married together. So from the beginning of Rain, we've been thinking about this problem, and we've been asking ourselves, what are the hardware substrates that we have to develop? And what are the algorithms that have to also be developed, and how can they fit together? So we've done work, at this point, I can say with high confidence that we are the bridge between the most cutting edge training algorithms, what comes next after backpropagation, and the most cutting edge hardware substrates, especially what we call compute in memory hardware substrates. And for the listeners that aren't familiar with that, compute in memory is this idea of doing your processing exactly where you store your data. And that's relevant to AI because that's what a synapse is. That's relevant to intelligence because that's what a synapse is. Synapses are both memory units and processing units. They store a weight and they modulate a signal that's sent from one neuron to the next. GPUs and CPUs fundamentally separate memory and processing. So one of the big consequences is just all this data movement. So you want to eliminate data movement. You want to co-locate memory and processing so you can build artificial synapses, and we call that compute in memory. So we have some of the world's greatest experts in compute and memory in our team and have collaborated also with like Stanley Williams, the godfather of the memristor. We wrote a paper with him that was published in Nature Electronics last November, where he is, one of the leader of, memristor development. But we bridged his hardware expertise to algorithm expertise and demonstrated training on a fully analog neural network about 10,000x more efficient than a GPU. Previously, we had worked with Yoshua Bengio, one of the Turing Prize winners for deep learning. One of his students, who's now a member of our research team, came up with an algorithm called equilibrium propagation. And we connected that theory of the algorithm to hardware to show that it was possible to train fully analog neural networks for the first time. And I should mention again, Jeff Hinton, he not only referenced us in that paper, but when he, the day after, reached out to us and still, I think, usually references us in podcasts to ask us if we could bridge his algorithm to hardware. So we are this bridge. You want to take new types of algorithms and find ones that are especially suited to these new types of hardware substrates, ones that minimize data movement, ones that work in ways that are more like the brain, and ultimately you want to integrate them together into circuitry, right? So it's not just about writing an algorithm in software, it's about baking that algorithm in, intertwining it into the hardware, so it is more tied together, but ultimately much, much, much more efficient.
And as I hear you describe this idea of radical co-design, algorithm, hardware, software, I sort of assume that the algorithm discovery, it seems like maybe leads a little bit. Obviously, there's things happening in parallel, but is that the right way to think about it? Is that it's led a little bit by the algorithm, and then that, of course, is going to influence how you think about the hardware substrate ultimately?
That's precisely correct. So what we recognize as possible in mathematical theory, well, we realize that first before we implement that in full hardware. For instance, we've pushed also further on another flavor of an algorithm called fast target propagation. And this algorithm is only possible in analog hardware because it exploits the inverse relationship between voltage and current. It's getting a little nerdy, but to do a one-step inversion, matrix inversion. For listeners, matrix inversion on any type of hardware is really hard, really expensive. You can exploit the nature of the physics to make this happen in a single step. Now, to build that circuit in a very reliable way, we need to have other developments and other breakthroughs, or at least advancements in kind of the memristor technologies to do that at scale. But we already have IP now on an algorithm that could basically take all of deep learning from 10,000 examples to like 10 examples to train. That's kind of what's possible on the theoretical frontier. That's our most kind of a frontier algorithm, this FTP algorithm. But so that guides us, right? So those breakthroughs in algorithms, whether it's how to do training more data efficiently or how to just train much faster, those insights come first, and then it's followed with, okay, what is the best hardware substrate available today that we can then extend to support the greatest degree of these algorithms and build them into great products.
Makes a ton of sense. I want to talk about where we are sort of today. But before we do that, one other question, just as we think about this idea of radical co-design, and I know, we touched a little bit on, cloud versus edge, training versus inference, all these ways we can sort of separate some of these issues. Do you think that this approach to radical co-design, is it more well-suited to solving the cost problem at the edge versus cloud? Is it universal? How do you kind of think about that?
I believe it's universal. Like the only way to so AI is expensive everywhere. I want AI to be cheaper on the edge so we can make machines intelligent, but we also need AI to be cheaper in the data centers so these do not consume, or insane amounts of energy, more energy than we have available, and have massive carbon footprints. But we are targeting the edge first as a company. We are going to market at the edge for a few reasons. One is because we are qualitatively enabling something new, which is training at the edge. Our substrate is very scalable, and we could build and will build data center appliances in the future, with these substrates. But we want to go where there's no solution today. And also we want to go where NVIDIA isn't really paying attention. They're not, NVIDIA they're delivering so well on their data center revenue that they don't have to think as much or serve as well the edge market. The edge market is more fragmented. You have your Qualcomm chips, some Jetson GPUs, different flavors of things, but there are so many opportunities at the edge that we can unlock and kind of be the provider for. That's where we want to first address and be to start the world's defining kind of edge AI infrastructure company. But because of the scalability of the substrate, because of the fundamental nature of the problems that we're solving, we will then be able to extend this to the data center. I just want to be a great business before we have to go head to head with NVIDIA.
It's probably a pretty good process as well, just like Radical Co-Design. So tell me a little bit more then about kind of where we're at today. Where is Rain on this, mission to build artificial brains?
Yeah, so we're 6 years in, a little over 6 years in, founded in June 2017. And we spent a lot of time studying our North Star and articulating, the research that's possible that gives us confidence in ultimately unlocking a 1 million X cost reduction for that long-term, fully analog, 3D, asynchronous artificial brain. But we're not building that first as a product. We don't have to build a 1 million X product first to be a great company. We're building something that is still very similar in principle, and gives a very, the same sort of qualitative result. So we're building it's about 100X. We say it's about 10X reduction in power, 10X improvement in speed, plus adding the qualitative addition of training. And we're building a digital chip that we'll bring to market at the end of next year. We're super excited about this chip. We have a few tape outs coming up this next year. But ultimately, this is going to be, I love my head of hardware. He calls it, this is going to be the Maserati of edge AI, right? Like when we bring this to market, it's going to blow people away because it'll be the fastest inference at the edge for computer vision. And it'll be the only platform that offers really robust fine-tuning, adaptation, and personalization for computer vision. And there are a lot of places that this can add value. I mean, from the obvious suspects like drones and augmented reality, these are systems that are power limited, they're space limited, they're heat limited. They want to do a lot more right there. And there are also computer vision models where, like AR, VR, I know I would love to see a future version of the Apple, Vision Pro that doesn't have a battery pack, and also that has such perfect latency that there's no discomfort for the user. So those are the kinds of things we're thinking about with our go-to-market product that we're intending that we'll be taping out this next year. And yeah, there's a lot of opportunities at the edge. There's so many places that people need better compute. We've been working with some cool folks, with some government partnerships as well, projects like a self-driving X-ray. So a lot of promising spaces there, but yeah, we're bringing to market. It's not just a chip, it's a platform. So we'll have this really, really highly performant chip for training and inference at low power, but we're also building a really good software stack for ease of use and ease of integration, because that's also a critical component of any new hardware.
And from a customer perspective, as they hear about this Maserati sort of edge compute for AI, are they coming to you with sort of specific problems and feedback and saying it would be really great if you could do this? Or are they just kind of gathering information? Is it still just so, hypothetical for them, I guess, until they actually see it in action that, they're not even sure what they would do with something that powerful?
It depends on the customer. We're talking to a lot of folks, and we've been talking to folks for years and have a good, finger on the pulse of what's needed in different verticals in edge AI. In some cases, some folks, they've been thinking about edge training and they have a very clear vision of what they want to do and how they want to implement, on-device learning for maybe adaptation for a drone that has to fly in different types of weather. You know, for some people, for a lot of people, because the cost of training has been so high, they've never even conceived of what's possible actually if they could have on-device learning. So we are also doing an education process with these customers. But one thing I can say is that, given the proximity now we have towards our next tape outs, next year I think is going to be a very exciting year for us. I think we have some design wins in the future coming up soon because we are right. I mean, we're finishing up our architecture. We'll be ready for tape out soon, and then I think the pilot's end of next year will ultimately be that full cementing moment. But yeah, again, it depends on the customer, but I'm very pleased to say that it's no one is the pain point of the cost of compute is essentially universal.
Absolutely. I have one question from an investor as we were talking about Rain a week or two ago. And he said, I hear about how incredible this technology could be. And it feels a little bit like quantum computing almost, where you can imagine, all of the incredible things that could happen, but it feels theoretical. And his question was, what's your sort of degree of confidence that this is actually going to happen? And I think you're sort of answering the question by saying we're going to have, product in market by the end of next year. But how do you address that, right? Like the potential here is so incredible. There's a lot of research that's gone into it. How do you think about actually the probabilities of success and coming to market and delivering on that 1000x and more in time improvement?
Yeah, it's so this is a big reason why when we started, we were looking at that North Star. A team of bright scientists, want to study the most elegant way to improve, something and build a 1 million X machine. But that's why we're now bring to market with this a chip that's about 100x better than an equivalent GPU, and that one there is zero theoretical risk involved in that. There's no open question whatsoever of can this work. It's at this point a sheer matter of execution on engineering. Looking forward from there, this chip becomes kind of the scaffold that evolves into our North Star. There are problems there that are more on the theoretical side that still need to be solved, tying the future algorithms into analog components, managing noise as you build out more analog circuitry within this so you can make it even lower power. But what we're bringing to market first, there is no theoretical question. And that alone and the family of products that we'll be able to build with that substrate will allow us to become a multi-billion-dollar company already. That is not even yet considering what comes down the roadmap later, when we get to 10,000 to 100,000 to million X. But there is some theoretical bar there. And actually, the last point of that I should say, I think the theoretical bar on that North Star is smaller than the theoretical bar for most quantum computing. I think, when I look at the feasibility and the proof points of analog computing, these are some real problems to be solved. Like, how do you manage noise at scale? How do you, control an unclocked chip that's operating in asynchronous manner? But compare that to the fundamental problems at scales that is required to scale up qubits. I think ours is an easier problem to solve. And and anyway, I think quantum is fantastic and will solve some important things, but we have I have more theoretical confidence or more confidence in the theoretical risk that we face on the long edge of our roadmap than I have in quantum computing.
I mean, we're going to see it in silicon in a year from Rain, so it's going to be great. You actually were leading right into kind of the last question that I had, which is, if you think about a world in 5 years where Rain has been successful with everything we've talked about today, what do you think that world looks like from an AI perspective? What are we doing and what is Rain powering?
Well, it's so much intelligence everywhere, so much capabilities for adaptation and personalization in all of our machines. this is a world where, I think within 5 years, I think we'll be addressing again AR, VR, drones, robots. This is a world where those machines will be economically viable and so intelligent that they will be automating a huge volume of our work and our labor. In 5 years, if we can realize this potential, I think we could bring down the cost of autonomous vehicles so that they are a practical business model, and we could see proliferation of autonomous taxis. I think we could, there are other challenges in the world of robotics as well, but this compute problem is the central one. But as a platform for robotics in 5 years, I think we could see construction robots. I think we can see plumbing robots, electrician robots. I want to see so many more personal helper robots. I think we'll see far, far more proliferation of drones and far greater capabilities of those drones. This is a world where it's like everything from wearable devices that give you, real-time feedback on your health, that are continuously learning and giving you kind of precise, dosing recommendation for your medication based on where you are that day. These are the kinds of possibilities. Smart homes and smart structures, smart buildings, the future of retail, all of this can only be unlocked with cheaper compute for artificial intelligence. So if we fully realize just the next 5 years of our roadmap, I think it will be a very, very different world, a far more productive world, a far more capable world, and a world where we'll actually have to grappling with questions of, now that we're automating this work, what are the other things that we should be doing as people? And I think it's a very important question that humanity will face.
It is. It's a fun existential note to leave on. I think human creativity is augmented by machines in many ways, and I think that'll mostly be true, even if we do have artificial brains that are powering some sort of AGI. I think there still will be a place for human intelligence. So it's a really exciting future. I'm glad you're building what you're building, and thanks for educating us about rain today.
My pleasure, Doug. Always enjoy it.